Alright, so we're just going to take a little peek here at the use of catalysts, catalysis, at least that's how I'm going to say it. And of course, catalysis is just simply how we can speed up the rate of a reaction by using a catalyst. And the definition of a catalyst is something indeed that does speed up a reaction, but it is actually not consumed in the reaction itself. You can recover it. And, we may see some examples where it looks like it's very hard to do so, but there is, in some way, shape, or form, you could recover the catalyst. It's not used up in the reaction. Why do we look at catalysts? Well, obviously there are many times when we want a reaction to go faster than it does naturally. But especially in the, chemical production world, for example, or in research, if you're researching a reaction that goes very, very slow, you can speed up reactions by increasing the temperature, we've seen that, and also by increasing concentrations, but that means you're using more stuff or you're using more energy in an effort to get that reaction to go, and that costs. So using catalysts, even though some catalysts may be expensive, we can run the reaction at more reasonable temperatures. We can use more reasonable amounts of reactants, and those catalysts can be reused. So it might cost a little to, purchase the catalyst up front, but we get our money over time because it can be reused. The other nice thing about catalysts is that they're often very specific, meaning they only work with certain reactions. So that's very nice because then you can just pinpoint exactly which reaction you want to go, and that catalyst will only work for it. And of course, this is very important in biology, and we'll talk a little bit about that at the end. And as you see here, of course, in biology, we call our catalysts enzymes, and they obviously help speed up a lot of our processes, especially like digestion. And so they're important to us there. And overall, though, how are these enzymes helping speed up the reaction? It's because what they're going to do is they lower the activation energy of the reaction. That's that nice energy hill when we're looking at our potential energy diagrams. So when you had a nice energy hill, then the activation energy was how much energy it took to get to the top of that hill where the activated complex would exist. And what a catalyst is going to do, as we'll see here, it's going to lower that amount of activation energy. And so the lower that amount, there's our bell, the lower that amount, the quicker the reaction will then proceed. And another way to think about it is it's providing an alternate pathway, an alternative reaction pathway, which is going to involve an alternative mechanism for how that reaction proceeds. Now, the important thing when we look at catalysts, and especially when we look at the mechanisms of a reaction, the catalyst is involved in one step of the reaction, and then it has to be removed in another step, meaning it goes in and comes out. And so here we see ozone reacting with a free oxygen atom. And when that happens, we get two oxygen molecules. And the catalyst to speed this up is chlorine. And this is what's happening up in our ozone layer. When we introduce chlorine, courtesy of our chlorofluorocarbons, it speeds up the breaking down of ozone. We don't want our ozone layer to disappear. But you can see how this is happening. Again, this is a proposed mechanism, is that ozone is going to react with chlorine. It's going to create this chlorine monoxide or chlorine monoxide and an oxygen molecule. Okay, and then that reaction intermediate, the chlorine monoxide, will react with the oxygen atom and create chlorine and another oxygen molecule. And so, yes, the intermediate cancels out of this reaction, but you see that the catalyst goes in and comes back out. And that's important for a catalyst. It goes in and comes back out, and that's how we know that it's not being used up in the reaction. So if we look at our little diagram here, and this is from page 561 of your book, without the catalyst, then we would see a very large activation energy, uncatalyzed reaction. With our catalyzed reaction, the activation energy is much smaller, and the pathway is at a lower energy amount, so this reaction will speed up. Don't worry about the little two bumps right now, although that means, that there's a two mechanism pathway. If it was just a single hump, then that would mean it was proceeding in one intermediate step, or elementary step, sorry. But don't focus on that right now. Just notice that the activation energy is much lowered for the catalyzed reaction than the uncatalyzed. Now, if our catalysis is homogeneous, that means that the catalyst is in the same phase as our reacting species. So if I have gaseous reactants and my catalyst is gaseous, that's homogeneous. If I have aqueous reactants and my catalyst is aqueous, homogeneous. Heterogeneous catalysis results when the catalyst is in a different phase. So a solid catalyst acting on gaseous reactants or in a liquid solution. For example, when we put that manganese dioxide into our hydrogen peroxide. The manganese dioxide was solid, hydrogen peroxide was an aqueous solution, and we saw the result of that catalyst reaction. The iodide ion can also be used as a catalyst to decompose hydrogen peroxide. And again, if you haven't noticed already, but yes, when we have a catalyst, it's written above the arrow in the overall reaction. And here you see the decomposition of hydrogen peroxide as it breaks down into liquid water and oxygen gas. And you can see, again, that the iodide catalyst is going in and coming out. And then we have our intermediate being formed here and being used here in our mechanism, so that we end up with our overall reaction. 2 of the hydrogen peroxides makes 2 water plus oxygen gas. Our heterogeneous catalysis can also be known as surface catalysis. This is kind of what's happening like in your catalytic converter in your cars. Catalytic converters convert yucca stuff to not so yucca stuff for the exhaust of our automobiles. And the most common catalyst in our catalytic converters is platinum. And here you see another diagram where we have ethene coming in along with a hydrogen molecule. They attach to the surface of the catalyst, the reaction takes place, and then ethane leaves. And you can see ethene, maybe you can't read that, but ethene is C2H4 because there's a double bond between the carbons. Ethane is C2H6. So ethene was hydrogenated because we added hydrogens across the double bond. But the important thing is, just to know the lingo, and if you come across this terminology anywhere, but surface catalysis means that the reaction happens on the surface of the catalyst, and then the products leave, and you can see that the catalyst is unscathed. It's the same before and after. Last thing here, okay, again, I'm not going to pretend that I'm the expert on biological reactions and enzymes, because I'm not. But our enzymes are protein molecules with molecular masses over 1 million AMU. Huge. And they have the ability to convert 1,000 or so reactant molecules to products in a second. So they are super duper important for our existence. Again, they are very, very specific, with each enzyme acting only on a specific substance. For example, lactose and milk sugar. Lactase acts upon lactose, and what lactase does is it goes in and snaps that bond, so we get just galactose and glucose out of, when we digest lactose. Okay, so it takes a complex carbohydrate, a disaccharide, breaks it down into monosaccharides that are much more useful for us. Of course, glucose, much more important to us in our biological processes than lactose. And so this lactase enzyme is what's responsible. So if you know someone who is lactose intolerant, that typically means that they do not have lactase. So they are unable to break that lactose down, passes through their digestive system kind of rapidly, and can have some bad experiences because of that. And so if they are slightly lactose intolerant, they can take a supplement that introduces the lactase so that they can enjoy the dairy products just like people that are not. Typically, they talk about enzymes doing the lock and key model. And so we have what's called the substrate. And the substrate is the substance that the enzyme catalyzes. So lactase is the enzyme, and the substrate would be lactose. All right, and so this is what's called the lock and key model, meaning that the enzyme and the substrate fit together perfectly like a piece of like puzzle pieces. Whereas if you had a different a molecule, or here we see sucrose, sucrose cannot fit into lactase. All right, it doesn't fit. So only lactase and lactose can go together. All right, oops, sorry about that. And so again, the overall riding factor is the formation of the enzyme substrate complex provides a new reaction pathway that has a lower activation energy. Again, that's our key. When we have a lower energy of activation, then our reaction will proceed at a faster rate. I hope this helps a little bit. Again, you can talk to your AP Bio teachers if you need more in-depth analysis on these enzymes. But again, our main focus for chemistry is the fact that our catalysts lower that energy of activation so that our reactions can proceed faster without having to increase temperature or concentrations to get the job done. All right, I will see you soon.